So now we want to consider the integrals involving exponentials, and the integral of e to the x is just e to the x again, right? It's its own derivative, it's its own integral. And then, of course, plus your constant of integration because it is an indefinite integral. So let's look at an example. We want to find the area underneath the graph of x e to the 3x squared plus 1 between 0 and 1. Well, remember that area underneath the graph is just the definite integral. So our area is just going to be the integral from 0 to 1 of x e to the 3x squared plus 1 dx. So here we've actually got, instead of e to the x, we've got e to a function. We have to make it look like this. So we're going to have to do a u substitution and simplify this guy. I see a function here, 3x squared plus 1, and its derivative would be 9x. There's the x. So let's let u be 3x squared plus 1. Then our du is going to be 9x dx. And so I like to multiply by what's missing and then compensate. So times 9 here, times 1/9 on the outside. So our 9x dx right there is our du. And this is e to the u. So we've got a 1/9 on the outside. Integral e to the u du. And then we have to change our limits of integration over here also. So if x is equal to 0, then our value for u, we want to plug that in here. 3 times 0 plus 1, which is 1. If x is equal to 1 up here, upper limit of integration, then our u is going to be 3 times 1 squared plus 1. So 3 plus 1, 4. So this integral is 1 to 4. So we got that 1/9 out in front, and then now antiderivative of e to the u is just e to the u, and that guy gets evaluated from 1 to 4. So you've got 1/9. Plug in the 4, plug in the 1, and subtract. So that'll be e to the 4th minus e to the 1, which is just e. And that's a numerical answer. We could simplify that by factoring out an e if we wanted to, but this is good enough.